Hey everyone, I'm back. So next up we got towards a lightweight software architecture for PX4 computer vision. It's a session by James Strawson. James is a senior roboticist at ModalAI, and he's calling in from San Diego today. Um, James received his PhD in robotics from UCSD, where he also taught classes on 3D printing, mechanical design, feedback control, and embedded systems. Wow. Before joining Model AI, James created the robotic cape and EduMeep development platforms, as well as the lip-controlled robot open source software package for the BeagleBoard.org Foundation. At Model AI, James enjoys designing lightweight control and navigation algorithms for robots that run on embedded platforms. All right, guys, let's hear it up for James.
Okay, you can hear me now. Okay, technical difficulties, that's to be expected. Okay, so some of the fundamental computer vision tasks that you're going to want to start experimenting with and plugging into the PX4 ecosystem is going to be crucially visual inertial odometry, so that you can do very precise position feedback control, as well as navigation in indoor environments. The Fiducial Marker Relocalization is the next step that's going to try and compensate for some of the shortcomings of a visual inertial odometry system, which is knowing where you are relative to the world around you, as opposed to just where you are when the odometry system started up. And then finally, you may want to use one of PX4's newest and nicest features, which is collision prevention. This is something that can easily be done with a stereo camera pair, along with a host of other sensors. But for this presentation, we want to focus on computer vision. And so I'm going to talk about how to use stereo cameras for this. Now, a big part of connecting higher level data, such as odometry, into PX4 is just plumbing. It's getting data from the right sensors to the right algorithms, and then finally into PX4 itself. Now, there's a lot of examples online that you can find around based on ROS and Mavlink router. These are great methods to get you started because there are examples available. However, if you're comfortable with it, uh, just reading and writing UDP and UART packets, that's something you can easily do yourself if you're comfortable with it. The more complicated step is keeping track of all of the frames of reference that the data comes in and the frame of reference that PX4 expects the data to be in. So ROS and TF2 are very good tools for keeping track of different frames of reference and moving data around between them. Or if you're comfortable, I can show you how to do some of that math by hand so that you can more easily optimize it or fine tune for your platform. And then finally, my colleague's going to talk about some of our experiences with an open source VIO algorithm, VinceFusion. So the fundamental basis for a lot of what I'm going to talk about all depends on visual inertial odometry. So here you can see a drone flying with no magnetometer and no GPS. This is purely based on visual inertial odometry. And as you can see, this allows for extremely good position control, as well as disturbance rejection. As I push the drone around, it's very stable and very easy to fly, especially in very tight indoor environments with a lot of backwash off of walls and furniture. So to get this to work, you're going to be taking data out of your VIO algorithm of choice. There's dozens and dozens of ROS options online that you can start playing with. But whatever you choose, that data has to be passed through to the PX4 Autopilot in the form of a Mavlink packet. And whether you use TF2 or other ROS tools or Mavlink router, you still have to make sure every step of the way that the data is correctly rotated and translated into the frame that PX4 expects. You have to choose the appropriate Mavlink packet for what you're trying to do, and you have to make sure that the data is timestamped correctly. If you're using MavROS, then MavROS is going to handle a lot of the time syncing for you. Otherwise, you're going to have to make sure to do the time syncing between your onboard computer and the PX4 Autopilot yourself. Now, your first option for Mavlink packets that you can send into PX4 is the vision position estimate. This is the first one that you'll see in the PX4 odometry documentation page. And it's extremely simple. You're just sending in the drone's position relative to the local frame in X, Y, and Z in meters. This is going to be like the NED coordinate frame, northeast and down, or since this isn't necessarily lined up with north, it's more appropriate to call the local frame aligned with forward, right, and down as the odometry system is when it boots up. You can also send in the roll pitch and your angles of the drone. Now, if you want to be a little bit more fancy, you can give the EKF2 Kalman filter inside PX4 more information to work with, and therefore give you much better precision control and accuracy by also sending in the first derivatives of the first packets, the velocities in X, Y, and Z, as well as the roll speed, pitch speed, and yaw speeds. Now, something very critical to know when you're sending this data in is that the frame of reference for the first derivatives are going to be in body frame, not in local frame. So while we say that the X, Y, and Z position of the drone is the position of the body in local frame relative to where it started up, the velocity is actually going to be the velocity of the body of the drone relative to where the drone is pointing. So a positive velocity in X is always going to be forward along the direction of the drone's nose, so wherever the drone is pointing, not the velocity along the local X axis. You can be very explicit with the frame IDs. So here I've used the example of the child frame ID being body frame and the primary frame ID being local frame. This is most likely what you're going to use. Now, once that data is going into PX4, I think you'll find the experience is very good as long as you understand this plot and understand exactly what it means to be sending data in body frame and local frame. So each of the green boxes here is a frame of reference. It's defining a coordinate system. So for example, the body, this coordinate system is aligned with forward out the nose of the drone, right, and then down. This is also centered around the center of mass. There is an option in the EKF2 parameters of PX4 to define the center of your visual odometry data as offset from the center of mass. However, if you understand all of these frames of reference and you're going to be doing rotations and translations in your VIO algorithm anyway, I think it's definitely worth going the extra step and making sure that the data is going in correctly in the first place, then you don't have to worry about tweaking PX4 parameters. Now, each of the blue boxes is going to be a transform. So that's going to consist of a rotation and a translation. Translation is a simple 1x3 vector, x, y, z, whereas the rotation can be represented as either a quaternion, a roll pitch yaw, or a rotation matrix. For simplicity of the math, I highly recommend just using rotation matrices. However, TF2, if you elect to go that route, will handle all of that in the background for you. So the data that you're really going to get out of a VIO algorithm is not this body with respect to local transform. It's actually going to be IMU with respect to the VIO frame. So the vast majority of VIO algorithms are going to represent the position of the IMU relative to wherever the IMU was when it booted up. Now, the IMU you use for visual inertial odometry is not necessarily going to be aligned up with the aeronautic coordinate frame forward, right, and down, nor is it necessarily going to be aligned with gravity. And so I highly recommend doing the next step of having another rotation to go from VIO's frame of reference to a gravity-aligned equivalent So this rotation between VIO and VIO gravity aligned will have no translation. It will simply have a rotation to correct for the angle of the gravity vector inside of VIO's frame. You'll then also have to rotate to local frame, which is most likely going to be the opposite of IMU with respect to body. So you'll have to undo this twice. You'll have to go from IMU to body and then VIO to local. And then this is an optional step to go between VIO and VIO gravity aligned. Now, once all of those are in place, you can start doing something a bit more advanced. So here we have the drone has started with the VIO frame purposefully offset and crooked from its landing pad. And I have a small Mavros-based node running, which has just told the drone to go forward and back a couple of meters along the line of whatever its x-axis thinks it is, which in this case is off crooked. Now, as it reapproaches the landing pad, the camera suddenly sees the landing target and has now made a correction to that offset. So the drone was flying in local frame before, which was offset due to the crooked VIO frame. But then as soon as it saw the landing pad, it's made a correction from local frame to what I like to call fixed frame. So local frame is going to be aligned with wherever your IMU was when VIO initialized, and it's going to be your job to calculate the translation and rotation between the local frame and fixed frame, which is defined by fiducial markers or some similar localization system. You could even use a GPS or a magnetometer to do this, but April tags are a very available open source method for doing this. Now, much like we had a chain of transforms and rotations to calculate out the body with respect to local frame, this is just a case of calculating this by multiplying the rotation matrix and transforming each of these steps. So you do multiply, add, multiply, add, multiply, add, multiply, add, and then finally you get back to this link. Now, the final sort of fundamental computer vision technique that you're going to want to play with is PX4's collision prevention feature. Now here we're using a stereo camera pair looking forward at the wall, and as you can see, it doesn't matter how hard I push the stick forward, the drone is not going to crash into the wall. So I can freely move back, but as I try to go forward into the wall again, it's going to prevent me. Now this is the collision prevention itself, and the processing of my radio control inputs is completely being done in PX4 right now. All I'm doing on the onboard computer side is transforms and rotations of the stereo data into the format that PX4 expects. So this is the data structure that you're going to want to keep in or send into PX4. And the data structure is very much going to look like a spinning LiDAR sensor. So it's called the obstacle distance, and it's Mavlink message ID 330. And it's a very flexible Mavlink packet. It lets you send in up to 72 different distances spanning around the drone. Now, you don't have to populate all of them. For example, here, the stereo camera pair that I showed in the last video is has a field of view of 65 degrees. And so if we split the 360-degree field of view up into the 5-degree increments, then we're only going to use the center 13 of those. It's helpful to know that these distances and the array that contains them starts pointing forward and then spins all the way around to the right. So here we have distance index 0 is pointing straight forward, and then it's 5-degree increments all the way around. If you want higher resolution, you can decrease the increment value to something less than 5 degrees, and then you can have, let's say, higher resolution in this forward-facing area, or you can just leave it as 5-degree increments, and then you'll see all the way around. Now, to get there, you're going to have to take the point cloud that you get out of your stereo camera and do more transforms and rotations. Primarily, you're going to have to take the stereo camera field of view, which is Z out of the lens, X to the right, and Y down, generally. Rotate that into body frame, and then ideally put that also into a leveled out version of the body frame. So in the same way that we had a rotation between the VIO frame and the gravity aligned VIO frame, we're going to do the same here, going from body frame to a leveled out version of the body frame. Now, a very easy way to do this, a very computationally efficient way to do this, is to take a vector which is pointing down along gravity, so +1 in the Z direction, straight down, rotate it by our rotation matrix, defining body to local, which is what we already set into PX4. If we take the cross product of those two, then what we're going to get out is 1/3 vector, the cross product, which is going to define the axis that the body has to rotate about to go from where it is now to being level. And then the 2 norm of that vector can be arc signed to get the angle. Now we have a rotation in axis angle format, which can very easily be rotated or transformed into a rotation matrix, a quaternion, roll picture, however you like to represent your rotations. This is a very computationally efficient way to do this, and it also works well for the VIO gravity aligned frame. Now I'd like to see just what you get once all of these are in place. So this is an open source Mavros based node that we have available on our website that sends in a smooth trajectory into PX4 that defines a Bernoulli's lemniscate, also known as a figure-8 pattern. And so this is sending into PX4 a position, velocity, and acceleration at 30 frames per second. And what you get is a perfectly smooth trajectory. Now I'd like to hand it off to my colleague, Hitendra Gangani, who's going to talk a little bit about the open source Vince Fusion project and our experiences getting it to work with PX4.
Thank you, James. And hello, everyone. So in the interest of time, I'll just jump right into it. So I will be talking about our effort into working on a open source BI algorithm called as Vince Fusion. And so we wanted to share our experience about the approach that we took, the changes that we had to make to get real-time performance, and the kind of problems that we ran into. So to begin with, what we did was we tried Vince Fusion on a regular desktop PC, but using our own ROS bags. So our ROS bags were collected on the system on which we eventually wanted to run Vince Fusion live with PX4. And the ROS bags that we collected were both handheld as well as in-flight. So the reason we took this approach was because it helps resolve a lot of fundamental issues like the extrinsic calibration, wherein you have to give the IME to camera relationship, the intrinsic camera calibration, feature tracking as to how many features you want are good enough, or what should the distance be between features, and anything that will help you get good feature tracking. Another important thing that we can tweak during this process is the IMU noise parameters, which is the axle and the gyro noise deviation and the bias. And while we are working on these issues, we also realized that there were certain assumptions that were made, like the focal length being of a particular value and the way in which the IMU only post generation was being done. So even though we were working on a PC with our ROS bags, we were able to iron out all the issues in order to get it working stably on a PC with our ROS bags. So once we had this consistently working, then we made the switch to moving from the PC to the actual drone on which we wanted to fly Vince Fusion with PX4. And then once we moved there, first step was to make sure that the ROS bags that work consistently on the PC works really well on the onboard computer as well. And then we moved from using the ROS bags to using live camera and IMU data. And since the PC is going to be much more powerful than your onboard computer, we had to deal with the real-time performance. And what we noticed was that if we are not performant enough, then the functionality also starts breaking down. So we had to resolve a lot of performance issues so that the functionality stayed intact. And some of the things that we did was to use GPU for feature tracking instead of the CPU, some optimizations related to Cirrus Solver, specifically in WinFusion. And then instead of consuming, let's say, features in every camera frame, we said, let's try and consume features from every other camera frame. And another thing was related to that we have just recently discovered is issues related to threading mechanisms. So we need to have very efficient threading mechanisms to gain real-time performance. So these were some of the performance issues that we resolved to get a good functionality as well. And the final step was to try WinFusion with PX4. And the first step was to send the WinFusion data to PX4. And the way in which we did that was using what James mentioned earlier, using the voxel vision PX4 that we have. So we sent the WinFusion data using that mechanism. And there were a few, the problems that we ran into when we did that was sending incorrect parameter for the VIO data, specifically, like James mentioned earlier, it was PX4 expecting the VIO data to be in a certain frame of reference, but we're not sending it in that frame of reference. So that's what I mean that here. And then as far as pose is concerned, it's sending the timestamp mechanisms wherein if you lag the pose by a lot as compared to the current time, then the VIO packets were getting dropped. So this is just a quick video of where we stand. This is using WinFusion in hold mode is what we are doing here. And one of the things that we are experimenting with right now is to update the pose using IMU data only, using a good camera pose as a baseline, but something that we have just been trying out recently. Thank you very much.
Thank you. So let's see what questions we have come up already. Good, we have lots of questions. Let me swap back to my video so you can see me. There we go. All right, so questions. What hardware do you use to run your VIO setup, i.e. computer, cameras, IMUs? So we develop and distribute a fully open source development platform called Voxel, which is based on a Snapdragon processor. And so that's what we use for all of our development. We have wide angle fisheye lenses, which plug straight into the camera ISP of the Qualcomm Snapdragon chips. And so we can get very high performance VIO out of this setup. Can VIO work outdoors with GPS fusion as well? Yes, VIO can work outdoors. You may want to configure it a little bit differently, just basic parameters of the VIO algorithm. GPS fusion with VIO is actually fairly recent development in PX4 itself, and I think we're going to see a lot of tweaking and performance improvements of that in the coming months, in the coming releases of PX4. Derivative doesn't work for discontinuity and corners. How to deal with that? So I assume you're talking about sending in the derivative of the velocity derivative of position that you're sending into PX4 for the odometry. Now, PX4 expects a continuous input, so you should have no discontinuities into the input going into PX4. If you need to handle any jumps, such as when you see an April tag, you need to make sure that the data PX4 is getting is completely smooth, and any adjustments you do to those offsets are taken care of before you send the set point into PX4. So PX4 always needs to be flying relative to local frame. If you have position set points in a fixed frame, you need to translate those set points into local frame first to avoid those discontinuities, since PX4 won't handle them. And of course, we can't have the first derivative of a jump. Have recent ROS versions dealt adequately with their software timestamping issues? Previous versions did not provide hard real-time guarantees on timestamps. causing serious issues with sensor drift in vision processing. If you're going to be consuming camera and IMU data through ROS, I think you'll definitely want to be very sure that the ROS nodes that you're using to publish the camera and IMU data handles the timestamps properly. So that's the wonderful thing about the open source community, is we release the ROS nodes that we all create, and it is the ROS nodes themselves which generate those timestamps. So it's really up to whoever's programming the node to do the timestamp correctly. That's not up to ROS. ROS just sends around the timestamp that it's given in the packet. So whatever driver you have reading that IMU is going to have to do the timestamping. Okay, question, XYZ position with respect to home position. Home position should be fixed then. Yeah, this relates similarly to a previous question where home position is wherever the VIO started up. And so anything that you want to move, anywhere you want to go relative to that, you're going to have to do a transform and a rotation to the set point so that you can't move that around. Last question, how to use VIO with GPS so the drone can enter indoors doing an auto mission. Isn't that the feature that everybody wants? So I think starting with PX4 1.11, VIO and GPS play a little bit more nicely together, but that's not something that I've done lots of flight testing with myself, but I think we're going to see a lot of development in PX4 with regard to this. So I think that's all of my time, and that was the last question. So thank you all for dialing in. I hope you found this informative. Thank you.
James, thank you a lot for your time and contributions to open source. It was a really cool presentation, and I'll talk to you soon. Community, wow, welcome. I see like everyone here. Let's see, I get people from Portugal, from Mexico, yeah, USA, UK, Slovenia, Finland, Brazil, Turkey, Colombia, India, Korea, Romania, Myanmar, Indonesia, Canada, Switzerland. Wow, thank you guys, this is awesome. Thank you for joining today. We have a full day of sessions today, so I'm sure you're gonna be busy. Next up, we have open source workflow for advanced vehicle dynamics. It's by Mac Bacanti and Jesse Hoskins by GE Aviation. While I load the speakers, please stand by. Don't forget to look for the pre-recorded sessions. They're on YouTube channel. Please go and search for those. There's some that are premiering right now as I speak. Pay attention to that, and please follow us on social media. Don't forget to post using the hashtag PX4 Dev Summit. All right, so be right back, guys.